Hello everyone. In this video we will be talking about the span of a subset and spanning sets. So in words, if we let S be a non-empty subset of a vector space V, then the span of S is the set of all linear combinations of elements from S. So more symbolically, using set notation, we have this. So basically we're allowed to gather any finite collection of elements from S, scale them by some scalar in R, and then add them together, right? And then we have all elements that look like that. That is the span of S. Now, we have a few important things to note. So here I assume that S was non-empty. So we do say that the span of the empty set is the zero vector space, or trivial vector space as we also call it, right? And so why would we set this up like this? Well, sometimes you'll see that the span of S is the intersection of all subspaces containing S. And since every subspace contains the empty set, and 0 is a subspace always, then this would be the smallest one and thus the intersection. So it kind of makes sense there. You can also just take it to be a definition. One reason why this is nice is that it falls into this result where we no longer have to really require that S be non-empty. So it turns out the span of S is always a subspace of your vector space V. So why is this true? Well, again, you want to think of the span as being the set of all linear combinations. So we're actually going to go ahead and prove this here. So let's remember, what do we need for something be a subspace? Well, first, we should have that the span of S is not empty, right? And this is always true, right? Because the span of the empty set is 0, which is non-empty. It has a 0 vector. And if it's non-empty to start with, well, then span of S definitely contains S itself, and so has to be non-empty. And then the second thing is that if you have two vectors and you can scale them and add them together, that this would still be in the span, right? If V1 and V2 are in the span. So what does this mean? Well, we're basically taking a linear combination of linear combinations. So it looks something like this, right? Because this is in the span of S, and so here we would have that the SI's and TI's are all in S, and our AI's and BI's are just scalars, and R1 and R2 are also scalars. And so basically you can just rearrange this, and it will look like this. So again, note that like these are CI's, right? These coefficients here, and then in arrowed in blue here, these are all vectors from our subset S, and so this is exactly fitting the definition of being in the span. Thus, it's in the span, and the two conditions are satisfied for being a subspace. So let's run through a few examples here just to get an idea of like what's actually going on apart from this abstract definition, right? So here's the span of the vector 1, 0 inside R2. We'll just assume the usual vector addition and scalar multiplication. So this actually is just the x-axis. So why? Well, we only have one vector here, right? So this span is going to just look like the set of things that look like C times our one vector 1, 0, where C is a real number, right? But I mean, this is exactly just C times 0, or C in the first coordinate and 0 in the second coordinate. And that's exactly anything along our x-axis, right? We have 0 in the y-coordinate and anything we want in the x-coordinate, okay? If we add 0, 1 to this collection, take two vectors in our set, then this actually spans R2. So this gives us the x-axis and y-axis, of course. But let's look at this from two ways. So geometrically, what's going on? Well, I have 1, 0 here and 0, 1 here, right? And then I'm allowed to scale these and then add them together, right? So if I just add them together right away, I would just get the vector 1, 1, right? But I can scale. So, you know, I can go 3 in the length of 1, 0 and up by 1, right? And so I could get something like this, where I get 3, 1. And in general, you can get just any point that you want. Why? Well, it's actually quite easy to see algebraically, right? So what does a general thing look like? It looks like some x-coordinate and y-coordinate. Well, this can always be written as the linear combination x times 1, 0 plus y times 0, 1, right? And so since these guys represent an arbitrary element of R2, that means this span is going to be all of R2. So basically these two vectors together generate a plane. So this is another example that I think is important to talk about here. So we know that the first two together generate R2. The addition to the third one doesn't really affect that. So I mean, it changes how you could write some linear combinations if you wanted to. For instance, right, you could write 1, 1 as either 0 times 1, 0 plus 0 times 0, 1 plus 1 times 1, 1. Or you could write it in terms of the first two, right? It would be 1 times 1, 0 plus 1 times 0, 1 plus 0 times 1, 1. But the point is, if you could already write everything in terms of the first two, you can still write everything in terms of the first two, and you could just have 0 as your coefficient on the third one. And so something that we'll be talking about pretty soon is linear independence, and basically that's going to be boiling down to like what is necessary, right? If I give you some collection of vectors and say it spans a space, does that necessarily mean that you need all of them to span it? In this case, we see that this 1, 1 is kind of redundant because the other two already get you 1, 1 as a linear combination of themselves. All right, so let's look at two more examples here. So 1, 0, 0 and 0, 0, 1. So this is a subspace of R3, right? But it's not going to give us everything because we never get a non-zero y-coordinate. So this happens to just be the xz plane inside R3. And down here, I just wanted an example that wasn't in Rn. So if we take 1x and x squared, basically another way to write this is anything in here looks like a plus bx plus cx squared. So this is exactly equal to P2, the set of polynomials of degree no greater than 2. So we've already gotten a few examples of these things, but these are called spanning sets. So a spanning set for a vector space is a set so that its span is the entire vector space. So again, we saw that R2 is the span of 1, 0 and 0, 1. Right, we saw we could even toss in the vector 1, 1, so this means that this set in here is a spanning set. For P2, in that last example, the span of 1x and x squared, basically allowing you to get your constant linear and quadratic terms. So again, 1x and x squared is a spanning set. Now, right, just 1, 0 by itself up here, that only gave us the x-axis, right? So the set 1, 0 is not a spanning set for R2, right? We could only get one line and not the whole plane, so we couldn't get everything. So that's all this definition is. So you're a spanning set if you span the entire space that you're within. So a natural question here would be, how can you tell if a set is a spanning set? So let's look at this through an example, okay? So, I mean, we saw one for 1, 0, 0, 1, but that's also just really, really easy because you're used to thinking of points in the plane as their x-coordinate and their y-coordinate. This example here, so it's still in R2, but it shouldn't be clear why any vector in R2 can be written as a linear combination of 1, 1, and 2, 3. So let's see why this is true, okay? So first of all, again, what does span mean? That means that everything is going to look like, and here I'm going to use this for a reason because we're going to translate this actually into a linear system. So it's some coefficient in front of 1, 1 plus some coefficient in front of 2, 3, right? Equals anything that I want. So I'll just say a general thing in R2 looks like AB. You can call it XY, whatever. Okay, well, I'm just going to go ahead and actually multiply and add these out, right? So this is x1 plus 2x2 in the first coordinate. And this is x1 plus 3x2 in the second coordinate is equal to AB. Well, this is just a linear system, right? Because I just have my first coordinates have to be equal, my second coordinates have to be equal. And we know exactly how to solve these. So let's figure out what x1 and x2 have to be to make sure we get AB. And if we can get any AB, right, that's just any element that we want in R2, then that means we span all of R2, right? We can get anything if we just choose the right x1 and x2. So that's the idea here. So now I'll just translate this into the augmented matrix. And we'll go ahead and reduce it. I'll just show all the steps at once. And we get this solution, right? So this tells us immediately that x1 should be 3a minus 2b, and x2 should be b minus a. And then with those choices, we can get any AB. And you could actually go ahead and plug them in yourself to see that it works. But this shows we can get any element from R2 as a linear combination of these two column vectors, and thus they span R2. All right, and to close up, here are your two exercises. So first, I want you to show that this collection of three vectors spans R3, i.e. is a spanning set for R3. And again, you should do that following kind of the method I just showed you and rewrite this as a vector equation, right, where x1 times the first vector plus x2 times the second vector plus x3 times the third vector is able to get you any ABC inside R3. And then for your second exercise, I want you to come up with a spanning set. And of course, this answer need not be unique. There are going to be tons of different ones that are possible, although there are definitely some that are more natural, for the set of 2x2 matrices and the set of diagonal 2x2 matrices, which I have an example below. That just means that only the entries along the diagonal can be non-zero. All right, thank you for watching.